Okay, so last talk for today, Katelyn Horstman from Caltech, speaking about searching for exo-satellites with Keck. If I find the slides, where is it? This one. Oops. Yeah. Okay.
Hi, everyone. My name is Katelyn Horstman, and I'm a fifth and final year PhD student working in the Exoplanet Technology Lab here at Caltech with Professor Dimitri Malway and an NSF Graduate Research Fellow. And today, I'm very excited to be the last talk of the day, talking about searching for exosatellites and brown dwarf binaries using the Keck Planet Imager and Characterizer, or Keck. So I think it goes without saying to a crowd like this, but studying hierarchical systems is important. It gives us insights into exoplanet formation and evolution from looking at different systems and their architectures, allowing us to do comparative studies between the constituents of the system and our own solar system, including planets and hopefully one day moons or satellites. And it also provides new places to search for habitability, especially around more active K and M dwarf stars, where we see that some of the radiation can be relatively inhospitable for some of these planets to end up surviving. So these can provide places that we can see protection. So Jason already did a great job summarizing earlier, but Keck, or the Keck Planet Imager and Characterizer, combines high contrast imaging and high resolution spectroscopy. And so if we know the position of our planet relatively well, we can take an optical or a single mode fiber, and we can isolate the light from the planet itself and feed it into a high resolution spectrograph. In this case, this is NIRSpec at the WM Keck Observatory that has a spectral resolution of about 35,000 in K-band. Once we have that planet light, we have a raw data of a model of the planet light that we see, a little bit of residual starlight that leaks into the optical fiber and the atmosphere of Earth. And we can make a forward model of the planet, star, and atmosphere and compare these two to get a detection of the planet and its properties using the cross-correlation function. And so for these RV measurements of directly imaged planets, we're really able to leverage the fact that we can isolate the light from the planet itself and look at its planetary spectrum. So how we look for planets around stars using the radial velocity method, we can look for moons around planets by looking at the planetary spectrum itself and seeing if there's a Doppler shift. And this allows us to leverage high-resolution spectroscopy, high-contrast imaging, and radial velocities all at once. And for the rest of this talk, I'm going to talk about two projects that I've been leading that have utilized these techniques. The first one being a dedicated radial velocity survey to look for exosatellites and place detection limits with Keck. And the second one being a spectroscopic brown dwarf binary survey to constrain orbits and provide formation clues. So we think exosatellites can form through many ways, through captures, collisions, but today I'm going to focus on the case of the circumplanetary disk, or the disk of dust and gas that we think surrounds a planet as it's forming. The typical circumplanetary dust mass relative to the planet is about 10 to the negative 4, which is the same mass ratio between the Galilean satellites and Jupiter. We believe that moonlets form in the disk from solids and eventually collide together to accrete to form things like moons or potentially binaries, but also may be able to accrete gas if they become massive enough. And even more massive planets may form more massive moons following the scaling relationship. The mass of the planet is proportional to the mass of the moon, or the mass of the moon is proportional to the mass of the planet to the 3 halves. And so in May of 2024, we started the first dedicated radial velocity survey to look for exosatellites around brown dwarf GQ Loopy b, which we've already heard quite a bit about at this conference. We primarily picked this object because it has a relatively high mass of about 30 Jupiter masses, which makes it likely to harbor proportionally more massive moons based on the scaling relationship that I mentioned earlier. And it also has other favorable qualities, such as a contrast ratio of 4 times 10 to the negative 3 in K-band, which allows us to get high precision radial velocities. But the most important reason we picked GQ-Loop-EB is it's because it's the only planet we know of, or brown dwarf, with a detected circumplanetary disk that may have a potential cavity in it. And so the way that we see planets forming gaps or cavities in circumstellar disks, we figured, could a moon potentially be carving out a gap in a circumplanetary disk? And so this image has already been shown at this conference earlier, but it's from Kuno et al. 2024, where we're looking at the spectrum of GQ-Loop-B, and we see with JWST MRS observations in mid-infrared wavelengths that we have quite a bit of excess. And so that can't be explained with only invoking the planetary spectrum, but also adding disks, which there are several disks that are able to basically do this and are consistent with the mid-infrared excess with Jupiter radii cavities between about 8 to 51 Jupiter radii. Oops. And so for our full RV time series for GQ-Loop-B, we were able to get 7 epochs of monitoring starting in May of 2024, the 4 of which we see that are the first 4 here are leveraged from previous KPIC data that we already had, where the rest of these are part of the survey. Each one of these boxes is its own epoch, which is between about 1 to 2.5 hours of observations, and each one of the colors represents the RV derived from a different order in K-band, primarily orders 33, 32, and 31. So we got about 20 hours of monitoring, about 22 hours total of observation, with an RV precision of about 400 to 1,000 meters per second, being the best in median, and we believe this was limited by the fringing that Jason talked about earlier, which I'm happy to go into more details about. And so although we weren't actually able to find any exo-satellites around GQ-Loop-B, we were able to place some constraints and some limits. And so what we were able to do with the previous RV time series that I showed before is we were able to run injection recovery tests using RV search to say, is there a particular moon to planet mass ratio and semi-major axis where we would see an RV semi-amplitude and be able to recover that 50% of the time, given the previous RV time series that I already showed. So focusing on this blue line here, which is KPIC line, we see for the injection recovery tests, at the innermost limit that we think a moon could possibly be stable, so before it would be ripped apart by tidal forces due to the Roche limit, KPIC is sensitive to about 0.6 the mass of GQ-Loop-B. And if we go out to the furthest extent of the cavity that we believe to be predicted from various models from Stockel et al. 2021, which is about 65 Jupiter radii, we find that GQ-Loop-B is about, KPIC is about sensitive to about 3% the mass of GQ-Loop-B. But the next generation of high-resolution spectrographs, primarily high-spec, which is planned to have first light at Keck in 2027, will be about 10 times more sensitive from simulations that we also ran. So we did a similar time series of around 18 hours of observation over 6 days, and we found that we could drop the RV precision from about 1,000 meters per second to 22 meters per second, really starting to push down the sensitivity to satellites that are between 10 to the negative 3 and 10 to the negative 4, which are starting to probe the masses that we would expect to see from material formed in the circumplanetary disk. Looking even further ahead into the future to first light instrument Andes on ELT and MODIS for TMT, we really expect to start to be sensitive to these solar system-like analogs. So if we were to directly image a system like GQ-Loop-B, so at a distance of about 140 parsecs away, and a mass of about 30 Jupiter masses, and an age of about 30 megayears, we can see that we will have an RV precision that is close to about, or less than 10 meters per second, which lends itself to being able to detect mass ratios between 1 times 10 to the negative 4 and 5 times 10 to the negative 5, which is really starting to probe these solar system-like analogs and the masses that we see of the moons in our own solar system today. So although the prospects for detecting exomoons with KPIC and these future high-resolution spectrographs seems really, really great, we thought, well, what can we do now with the current data we have before these other instruments go on sky? And as was talked about earlier, KPIC has already been able to detect about 30 substellar companions, all of which we could see in boxes on the screen here for CCF detections. And we wanted to do a 3-year monitoring program to study a minimum of 10 targets and get 1 epoch per year of the brightest KPIC companions and those that have strange CCFs. So I've highlighted some of those here for us to look at, of some, again, the brighter ones with higher SNR, and maybe ones that have double peaks in their CCF, which could indicate it could be a spectroscopic binary. We wanted to look to see if we could detect any of these binaries, so we could study them based on occurrence rate and separation of the binaries, where we're looking at their mass ratios and their distances to their host stars. So assuming from angular momentum conservation that these younger and further away systems would have wider orbits and binaries. And even if we aren't able to detect any of these objects to have binaries, we're still able to get radial velocities, which will help constrain orbits and eccentricities. And so these are just some preliminary results that we were able to get from the brown dwarf binary survey. Just as a reminder, for each of the orders here, we only have order 33, so particularly in this band. And each of the different fibers is indicated with different markers here. And we can see a range of all of the different objects we were able to target with this particular KPIC survey. And so we were able to get 3 epochs for most of these with SNR higher than 5, but we're still working on the data reduction. As was alluded to in many other talks, in the data processing talks, there isn't one size fits all for doing these types of surveys. So this is from looking at the pipeline itself and basically auto-reducing the data that we were getting. And now we really have to take a look at the quality of the data, take a look at the fringing in each of these individual constituents, make sure the wavelength calibration is correct, that we have correct telluric models before we can say anything definitive about whether or not any of these systems may contain a binary. And I just wanted to give a big shout out to the KPIC team, which Jason also talked about earlier, all of which this work wouldn't have been able to do without them. And also plug some other KPIC high-spec talks and posters. The talk that Jason gave earlier in the session, he also talked about all of the different KPIC posters, but I also wanted to highlight one high-spec poster by Nieti, which is also going to talk about development for high-spec specifically, since KPIC is a pathfinder for this instrument. And with that, I will leave up my conclusion slide and take any questions. Thank you.
This is so fun. Thank you for doing this project. I'm curious, one of the limitations with RV for finding planets is knowing our stars and how they change really well. Are we going to have problems with like weather on planets, or do you know what the limitations are from that?
Yeah, so I've thought a little bit about this, and at our, kilometer per second precision, this isn't really a problem. But as we start pushing down to do maybe PRV or EPRV of things like brown dwarfs and planets, I imagine there's some work on kind of like Doppler monitoring of these systems and clouds. Once we have a better idea of that, I think that is something, the variability from that we'll have to start incorporating into these models. But I imagine that will probably start to be an issue closer to tens of meters per second or meter per second precision.
Yeah, great talk, really exciting results. I was curious if you, kind of related to Rachel's question, if you have looked at like age as a factor in some of your objects, because like you have like DH tau B, which is a really young system, and even if it's not necessarily weather induced, you could see like radial velocity variation that's quite large from activity and other things.
Yeah, for this particular survey and looking at particular objects with KPIC, since they're directly imaged, we mostly focus on these younger and brighter systems. But I think that taking a look at how this changes with age is also something that's really interesting once we have access to these like cooler, older planets, which some of the people have and folks have been talking about here. And I think that there are some good candidates to start looking around.
Thanks.
It looked maybe in your GQ loop B like there were systematic offsets between the different orders. Is that real? Or?
Yes, and so this is actually something we're actively working on looking at KPIC with all of the data that we actually have, and something we talked about at the decommissioning. We see that there's differences between particularly like orders 33, 32, and 31, where that trend is upwards, and also differences between the fibers. And so we're trying to figure out whether that is the way that we calibrate the wavelength solution independently for each one of those orders, or if there's something else that we need to incorporate. Also historically could be due to fringing, and there's lots of different things we need to look at about why there's a drift between these particular items.
Thank you. So great talk. I'm Masai Kuzuhara from Astrobiology
I do not see
Center
where
in
you are,
Japan.
I'm sorry. Oh, okay, thank you.
Yeah, I'm here. So yes, I'm Masai Kuzuhara from Astrobiology Center in Japan. You predict that using high specs, you can get much better result. So, so what is the main factor for the improvement when using high spec? Is it wavelength coverage or throughput?
Yes, and so it's both of those. I think the three biggest things are that we're going to have much higher throughput. I'm not going to say a number. I'll defer to Dimitri because I don't know what the latest numbers are for high spec. What I'll also say is that we're supposed to do YJHK simultaneously. So that'll provide more wavelength coverage. And also high spec is supposed to have a resolution of 100,000 on average for all of the bands compared to 35 is what we're getting right now.